Unit 9.7, shifting gears from what we've been talking about before. At least it seems like we're shifting gears, but not really. It's equilibrium, it's energy, but in this case, we're going to revisit some of the oxidation reduction things we did earlier in the year and show how we can utilize those reactions to actually provide energy for some sort of work. So they're going to be called galvanic cells. We're going to make these actually in the lab also. No, not with lemons, but we will use metals. This looks like a nail, which has primarily iron, and this looks like a penny, and at least on the surface of the penny is copper. And we're going to use metals like that along with ions inside this lemon. No, there's not iron ions and copper ions, but you can still make a type of a battery, we'll call it, but a galvanic cell in there. Of course, you can go buy AA, AAA, 9 volt, so forth batteries, and inside of those are galvanic cells. But they are thermodynamically favored reactions, and they're going to generate electricity by the movement of electrons. So we're going to use something called E, and we're going to often use that postscript like we've used before for standard conditions. When you have redox reactions, you know that you'll cancel the electrons. That's nothing new, but that E means electromotive force, and those electrons that get canceled in that balanced chemical equation, something lost electrons, something gained electrons, that number of electrons, that number of moles of electrons are what is going to provide the energy that we're going to deal with. And we're going to talk in terms of volts for that. We're going to use a table in our textbook, or on tests I'd provide you with an abbreviated table, or you can Google a table of, they're called standard reductions, and the reason called standard reductions because they're all written as reductions. So here is a reduction half reaction. Here's a zinc half reaction, and they're all written as reductions. Now, in any particular chemical reaction, one item will be reduced, the other item will be oxidized. So one of these in the table will always have to be flipped to make it look like an oxidation. We're assuming 1 molar solutions and 25 degrees Celsius. That's standard with these reduction tables. They're all relative values, these voltages that are in these standard reduction tables, and they're all based off of the potential for hydrogen. Okay, so if it's better reducer than than hydrogen, it'll be values above 0. There's ones below 0, so forth. I don't think this is provided to you in your equation sheet, but we're going to be using this over and over and over again. We'll often be solving for E cell. That's basically the voltage that's going to get, that we're going to get provided to us by the how we combine these items in a galvanic cell. There will be a reduction number and there will be an oxidation number. When you subtract these two numbers, you must get a positive answer. If you get a negative answer, it will not be thermodynamically favored. That would be kind of like the thermodynamically favored would be kind of using the battery that's in your cell phone to do all the things to power your cell phone. And then if you want it to go the opposite direction, that's not thermodynamically favored, and that's where you plug in your cell phone battery. I'll give you a couple numbers here. This is the E-cell half cell voltage for copper, and this is the half cell voltage for zinc, at least for these two half reactions. And so if you assemble these the wrong way, if you put the negative 0.76 in the reduction part of it, you will get a negative answer. But if you change this and you put the 0.34 minus the minus 0.76, you will now get a positive answer. And so that is how you are going to determine what item gets reduced and what item gets oxidized in a galvanic cell. When we produce one of these galvanic cells on a piece of paper or in the lab, we're going to want to be cognizant of, or if it's on a piece of paper on a test or a quiz, we're going to want to make sure we write all these things down. We need to define which item is the anode and which item is the cathode. And I already told you how to determine that, but I didn't tell you what the definitions of anode and cathode are. So the anode is the item that gets oxidized, and the cathode is the item that gets reduced. When I say item, the half reaction involved with oxidation, or the half reaction that involves reduction. The way I keep these straight is an A and an O, both vowels. The C and the R, both consonants, but whatever way you want to keep that straight is up to you. But it will be important to remember what is the anode and what's the cathode. We're going to make sure there's a wire that connects these two half reactions, and I'll show you how to do that in a second. And that's where the electrons are going to flow. And it will be moles of electrons. Okay, and they're always going to flow towards the cathode because the cathode is what is being reduced. So in this case, 2 electrons will be flowing towards the copper half reaction to make the copper ions become copper metal. We don't know exactly what this is all about yet, but we're going to have to put a salt bridge in there. And the salt bridge will help balance charges. Without the salt bridge, your circuit is not complete. And once there's a buildup of charge, meaning that once any electrons travel from one side to the other and something else doesn't replace that charge, it breaks down and it stops working. Basically, you would not even see it begin to work. So if you didn't have a salt bridge, or there's some kind of other disconnect there, you would have no voltage. So basically, now this is a better artist depiction than what you need, but this is what you're going to have to draw on a homework question, on a test question, so forth. So let me kind of circle, or you know what, I'll highlight the important components. So here is a voltmeter, and it has a voltage of 1.10 volts. And actually, this is the 2 half reactions that I mentioned earlier in the unit here. We have actually we didn't. Oh no, I was going to write cathode and anode, but they're in there. They're right there. Okay. So you need to label which is the anode and cathode. You need to have a wire, and that wire should actually say how many moles of electrons. And how do I know it's 2 moles of electrons? That's how I know it's 2 moles of electrons. The copper gains 2 electrons, and the zinc loses 2 electrons. Okay, so what else do we need? We need, you know what, I'll circle this one in here. We need the ions that are in the chemical reaction. We need the metals that are in the chemical reaction. And we need to show how these electrons are either being lost or gained. So the copper is gaining 2 electrons. So the copper ions become copper metal. And then it's the opposite. Zinc metal is becoming zinc ions. So that's almost done. But then we also need this salt bridge. And the salt bridge is going to be composed of ions that, one, do not have any impact on the chemical reaction, meaning that they won't react with copper metal, copper ions, zinc metal, or zinc ions. And so things that are typically spectator ions are terrific for that. So any ions in the first column are awesome for those typically. Potassium, no problem with that. I think most people end up using, for no other reason than just people do things the same. But often I see potassium ions, but there's no reason why you couldn't use sodium ions. And then this is risky to use sulfate. Not with this particular reaction, because sulfate won't precipitate with either of those ions. But sometimes, depending on what you're using in your beakers, sulfate could end up precipitating something, and you don't want any other reactions to occur. So I try to use something that is soluble with everything, like nitrate. There was no reason why you couldn't use sulfate in this one, but I would say, to kind of not have to think about too much, I would always use a alkali metal ion and nitrate ions every single time, and you would never run into a problem. But here's what's going on with these ions. As electrons come over here, this side would build up a negative charge. So something has to happen to alleviate that. And it turns out that many things happen, but one that happens is that cations go in the beaker. That would balance that charge. You could also lose spectator ions that are in that beaker that have nothing to do with the chemical reaction, but they could leave. And that would also alleviate that charge. And then the opposite is happening over on the other side. Okay. This is a little fancier than what you need. This looks three-dimensional. I think 2 dimensions are going to be fine. We'll come back to practicing that. You might run into something called line notation. So we just have to be familiar with what that means. So here would be a full chemical reaction, and no one bothers writing that because most of the things, well, not most, the nitrates in there aren't part of the chemical reaction. They're just spectators. And instead of writing everything out with pluses and arrows and all that, some people do this. Magnesium metal going to magnesium ions. That's 1/2 reaction. This might designate like, let's go back to our picture. That might designate sort of like that area there, okay? And then we have aluminum ions going to aluminum metal, and that's that there. Magnesium to magnesium ions, that is oxidized, and then aluminum ions to aluminum metal, that's reduction. So this is just me sort of helping you define what's actually going on there, but this would be the actual line notation. You're not going to be asked to write line notation, but you might see line notation and have to understand what it means. So let's jump in. Let's try one of these. Draw a galvanic cell with zinc and copper. So we already know a couple things. We know from our standard reduction tables, and I had already written these out, that these are the two half reactions that deal with copper and zinc metal. Okay, so now we need this to happen. We need that to be positive. So the only way we're going to get that to be positive is if we put the 0.34 first and the negative 0.76 in the back, and that's going to equal 1.10 volts. So our voltage, standard state, if we have 1 molar solutions at 25 degrees Celsius, we'd have a voltage of 1.10 volts. So what do we need to get this to be 100% on a test? Well, we need 2 vessels to contain these half reactions. It's kind of random which one you put on the left and right. What's not random is whatever one you put first, you have to know that it's either the anode or cathode. So, you know what? Let's do this also before we move on. You know what? I'll put it over here. So we said that this was the reduction and this was the oxidation, because that's the equation. Reduction minus oxidation is a positive answer for E cell. So what is the reduction? Looks like that is the reduction, and then this has to be the oxidation. So copper ions plus zinc metal, because you need that to be oxidized, becomes copper metal and zinc ions. Okay, so let's make this one copper, and let's make this one zinc. Okay, so if we make the one on the left copper, then we need copper ions in there. Technically 1 molar copper ions. I just don't have a lot of room in here to fit all that. I guess I could fit it in there. 1 molar. We need to show what's going on. The copper ions become copper metal. So there's a little arrow that way. The other one is zinc metal to zinc ions, a little arrow that way. We need to connect these up. So here's our wire. And the wire could just literally connect, but I like to put a voltmeter in here and show that it's making the voltage that it's supposed to make. We need to show which way the electrons are traveling. They always travel from the reduction to the oxidation half reaction. Whoops. We have to go towards the reduction, and I shouldn't call it the reduction, I should call it the cathode. And if you do cath and anode, that's probably good, but let's write that out. And that's still not going to work. Still not going to work. So what else do we need? We need the salt bridge. And the salt bridge is a vessel that allows ions to transfer back and forth. And I don't have a ton of room to write out ions inside the salt bridge. So it is okay, it's accepted to write those ions outside of it there. And that would be a completed galvanic cell, and you'd be able to get full credit for that. Okay, before we move on, what would we see happening? So reactants would go down in concentration, or grams if it's a solid, and then products would go up. This is blue. So the blue color over on the cathode side in the solution should get faded away over time. None of the zinc ions don't have a color associated with them, so you're not going to notice that. The zinc metal should get pitted, and you should see it kind of getting eroded away. The copper metal, it's going to be difficult to see it getting bigger, but if you wait it before you start it and wait it when you're finished, you would see a gained mass. Okay, so let's do the same thing again, but now here's our items. So which items deal with, which of these half reactions deal with those? So we need tin metal and tin plus 2 ions. Well, it's this one. So I gave you all these other ones because I just wanted you to make sure that you have the ability to pick the ones you're supposed to pick. We need iron plus 2 and iron plus 3, and it's right there. Okay, so E cell has to be a positive answer for a galvanic cell. Whoops. Okay, 0.91 volts. So that tells me that the iron is the reduction, the cathode, and the tin is the anode. So same kind of deal. We got our 2 beakers. We have our piece of tin. We have iron ions and iron ions. Well, what do we attach? What kind of solid do we attach this wire to? Well, you need a wire in here. You need some sort of solid material to be able to conduct this electricity. But it's not iron metal, because we're not using iron metal. We're iron plus 2 and iron plus 3. So we need some kind of metal in there, but something that won't react with anything else. And when you are given a situation like this, often people use platinum wire. Platinum wire is extremely expensive. So if you don't have any platinum wire, you could also use a carbon rod. That's the El Cheapo route. It doesn't cost as much, works fairly well, and it doesn't react with any of the items that are in the galvanic cell. But we're on a piece of paper here. Let's go not the El Cheapo route, but let's go the expensive route with the piece of platinum. So we got our wire, and here is our galvanic cell. No, not galvanic, sorry, our voltmeter. And we're going to put in 0.91 volts in there. This is sort of random that it's cathode on the left and anode on the right, other than I've already written tin in there. So I guess that's not random. Tin plus 2, yes, 1 molar solution. This is our oxidized, so the metal has to become a cation. You have to lose electrons. Now, I didn't actually write out the chemical reaction here. Tin metal, iron plus 3 goes to tin plus 2 ions, and iron plus 2. Now, that's not going to balance unless you do that. And how did I know to do that? Because 1 electron, 2 electrons won't cancel, so the entirety of the iron half reaction has to be multiplied by 2. So 2 electrons are transferred, and it's always from anode to cathode. We need iron plus 3 in there, 1 molar, and iron plus 2 in there, 1 molar. And it's the iron plus 3 going to iron plus 2, and it's happening at the surface of that platinum wire where the electrons are coming in. We're almost done, except we need our salt bridge And you may remember that my go-to is potassium nitrate. And that would satisfy. Okay. Predict what will occur when bromine is added to a solution that has that in it. Oops. Okay, so here's our beaker. We have chloride ions, we have iodine ions, and we're adding Br2. This is actually the activity series, and the reason I threw this in here is because these standard reduction tables are actually activity series. So the activity series that you may have learned went like this. F2 would be the most active, I2 would be the least active, and then I'll show you this. If the diatomic is super reactive, its ion is very unreactive. They're always opposites. So it looks to me like I minus is the most reactive, and let me erase those circles there. I minus is the most reactive ion. So if you take Br2 in there, Br2 plus 2I minus would give you 2 Br minus and I2. Okay. So I could use the ideas of the activity series. You could also go get, I don't have the half reaction voltages off the top of my head there, but this particular setup with the bromine and iodine would give you that. If you did it with the Cl minus, it would not give you a positive E cell. It would give you a negative E cell. And that will that'll get us started with galvanic cells.